All right, 5-2C, 5-2B, sorry.
Hey, Victoria.
Hey, Victoria. Hope you guys won.
No, not Trevor.
Increasing. Is it North Korean barbecue or South Korean barbecue? Because I probably wouldn't eat North Korean barbecue. Oh, they don't? They're not allowed to have any delicious food?
Hey, didn't Kim Jong-un say, like, this is also recording?
Increasing and decreasing functions.
It was going to get flagged from a church.
Yeah, that's okay. I've said worse, right, Kevin? Okay. Here we go. Increasing and decreasing functions. Now, you know, like I know, that if you were given a graph that looked something like this, and in ham or ram, whatever you decided to take, you had to find out what intervals this function was increasing and decreasing at, right? So you'd go to here, and let's call that A, and then let's call this B. And so this graph is increasing on the interval from -infinity to A. You can include A if you, I don't know. I'm kind of interested in that. I think this book likes you to include A, okay? And then you are decreasing.
Well, you have to B to infinity?
Yeah. So you're increasing from -infinity to A, then you're decreasing from A to B, and they'll put a bracket around that too. And then you're increasing once again from B to infinity. Dang it, I'm so used to writing it as a curvy bracket.
So it's okay to have two brackets?
Yeah, I know, it is. That's what they say, so I go with that. Okay, and you can see that from a graph. Now, what's going to happen is we're actually going to use the derivative to find out where graphs are increasing or decreasing, okay? So, here's what we're going to do. There's a corollary of the mean value theorem. Corollary. I know it sounds weird, huh? It says this. If f is continuous on the interval from A to B and differentiable on the interval A to B, okay? And it's like a big deal that it has to include A, B in continuity, but in differentiability you don't have to be including A and B, but whatever, who cares? All right, here's what it says. Then, if f prime is greater than 0, if the derivative in that interval is positive, then f is increasing on that interval. Okay? If f prime is positive, then f is increasing. And if f prime is negative, then f is decreasing. Okay? And we know that when f is 0, then it's a critical point. F prime, sorry. So we already know if f prime is equal to 0, then we have a critical point. Not necessarily a max or min, but a critical point. So here we go. We're going to do, I don't know, we'll see how many we want to do. Number 1, we're going to start with a very easy problem, okay, where we can actually visualize it. Now, you won't get your calculator for this. Sorry. So let's go ahead. We're going to analyze the behavior of f of x equals x squared. Now, I take your calculator away. You're like, fine, I'll just graph that in my head, which you can, I hope, by now. It's just a basic parabola. But it's going to ask you where are any extreme values, and where is this graph increasing or decreasing. Okay? We're going to use the derivative to find out all these things now. So first thing you want to do is you want to take the derivative. And the derivative would be 2x. And then what you do is you take 2x and you set it equal to 0 to find any extreme values. And you divide by 2 and you get that x equals 0. Now, I like to put these on a number line because that helps me with my intervals. And so this breaks it up into 2 intervals. I have an interval on the left, which is negative infinity to 0, and I have an interval on the right, which is 0 to infinity. And what I'm going to do is I'm going to test these values in my derivative. Okay? So I'm going to pick a value for x over here. What value would you like to pick? Over on the left side of 0. Negative 1. Perfect. You could pick whatever negative number you want. You want to pick negative pi? Go right ahead. I like to pick easier numbers, so I'll pick negative 1. And I plug it into the derivative. So f prime of negative 1, and I don't care what the answer is. All I care about is what the sign is. So when I plug negative 1 into this f prime, I get what? A negative. I get a negative number. And that means that my function is decreasing in that interval, in the entire interval.
If it was positive, that's increasing.
Okay, so let's go over to this side now. Yeah. X equals 1. Let's pick 1. 1's an easy one to do. You plug it into the derivative. F prime of 1 gives me a positive number, gives me 2. That means that my function is increasing. Okay? So if a function is decreasing, this one is decreasing from negative infinity to 0. It's decreasing. And then from 0 to infinity, it's increasing. And if something is decreasing on the left and increasing on the right, then perfect. X equals 0, or you can even say the point, 0, 0 is a minimum because it's decreasing over here and it's increasing over here. Now think about what the derivative is. Remember, I said this like in my Algebra 2 class to kind of make them feel silly, but I'm like, oh, the derivative, and they're like, what's the derivative? I said, well, it's the slope of the tangent line. Well, what is the value of any tangent line on this side of the graph? What's the slope of it? Negative. Over on the other side, what are the slopes of all the tangent lines over here? They're all positive. That's why when it's increasing, it's positive for the derivative and negative when it's decreasing. Okay? All right, let's do another one, number 2. So that one's pretty easy because you could have just graphed it, and from your skills from pre-calc last year, advanced math, you knew where this graph was increasing or decreasing. But what if I gave you a harder one like this? F of x equals x cubed minus 12x. And I said, no, you can't have your calculator for this. Now, you know what a cubic function looks like. They look like different things, but you are going to only do like calculus ways to find out where this graph has any maximum or minimums. The book will say extrema. I don't really like that word very much. It's just a weird word. And then you're going to find out where this graph is increasing or decreasing. Okay? So here's what you do. And it'll say analytically analyze the behavior of blah, blah, blah.
Analytically
Uh-huh, it does.
how?
Analyze analytically.
That says use analytic methods.
Analytic methods. There you go. All right, so take the derivative first. It seems like that's all we do in calculus, right? We take the derivative of everything, all the things that we take the derivative. And take the derivative and you get 3x squared minus 12. And then set that derivative equal to 0 to find any maximum or minimum or just critical points equal to 0. Add 12. Divide by 3. X squared equals 4. Take the plus and minus square root. Oh, Trevor too. Oops, hey Trevor. He's probably not watching. Okay, x equals plus or minus 2. Hope you guys won too. Okay. All right, so now, those are my critical points. And this is what I like to do. I like to split them up on a number line, -2 and +2. And these are my special points where f prime equals 0. And then I like to plug in numbers in each interval. This one broke it up into 3 intervals. Do you see that? Okay, so let's pick a number over here. Yeah? Into the derivative, yeah. Okay, I know, that's why it's really gets a little confusing. Like, am I plugging it into the original? No, I want to see where the derivative is positive or negative. So I'm going to take f of, let's do -3, or f prime, sorry, f prime of -3. So I plug it into f prime. -3 squared is positive 9 times 3 minus 12. I don't even care what it is, but I know that it's positive. Okay. A good number to choose between -2 and 2 is?
0.
Yeah, 0. And when I plug it in, 0 minus 12 is negative. And I keep writing f of 0, but that should be f prime of 0. And then finally, f prime of 3. 3 goes in, square it, blah, 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 and you get positive. Okay, so from this, we know that on the interval -infinity to -2, this graph is increasing because the derivative's positive there. Slopes of all the tangent lines are positive, so it's increasing. Bless you. From -2 to +2, this graph is decreasing. And then from +2, I'll just write it up here, to infinity, it's back to increasing. And then what they want you to do is they want you to find the points. Okay, so we need to then plug -2 and 2 back into the original function. Yeah.
We have to find the points, or we have to find out the maximum?
Yeah, the points that are the maximum, yeah, we have to find both.
Okay, because like you can just look at that and know that.
Yeah.
-2 is the maximum.
Uh-huh. You can actually, we can graph this. After we're done doing all this, we can totally graph this too.
Yeah, but like, do we have to actually find the point?
Yeah, they might ask you for the points. That's kind of hard to do without a calculator sometimes. So you're going to have to evaluate f of -2. You plug -2. This one's not too bad. It's -2 cubed minus 12 times -2. 16? 16? Okay. And then f of +2 is 2 cubed minus 12 times 2, -16. All right, so at -2, I'm increasing on the left, and I'm decreasing on the right. So if I'm increasing on the left and decreasing on the right, it looks like that. So that would be a maximum, and you can tell it's +16. So this is a maximum. And this one over here, at +2, I'm negative on the left and positive on the right, which means I'm decreasing on the left, increasing on the right. That would be a minimum. Everything's all jumbled together. Okay? And you can actually graph this now if you wanted to. You could figure out, you have 2 points. You know where it's increasing, where it's decreasing. Okay, you go -2 all the way up here to 16. +2 all the way down here to -16. Okay, this graph goes like this. There you go. I don't think it goes through 0, 0 though. It actually goes through -12 at 0, but it's close enough. And you can see how it's increasing here, decreasing in the middle, and increasing there. And polynomials will do that. It'll like go positive in one interval, the next interval negative, positive, negative.
Yeah.
Sometimes they don't though. Let's do one that doesn't. Would you like to?
Like,
Yeah.
good at actual math, like, 'cause we
Yeah.
have, computers. We don't get our calculators, so we have to know like.
Yeah.
Like
I could just ask you for just the x values of those.
Like
Yeah.
if it's a harder one.
Mhm.
Okay.
Yeah, and you would do that.
I'm not good at it.
This is number 21 from the homework. If you do it now, you won't have to do it later.
So you skip that one?
Yeah. Well, I want to see it on your, well, it's probably not going to be on your paper, is it? There's a lot of people that aren't doing this right now, and they're not going to get to skip it. No offense. I don't want to bother you. I'm sorry. I don't mean to interrupt your iPad usage. Sorry, Josh. I'm sorry.
Just copy it down.
No, you're taking notes. I know. I know.
We can just copy it down on our paper.
Oh, okay. No. That sucks. And good at the same time. Good. I'm glad you're dumb. Okay, here we go. Letter A. I don't think you're dumb, though. You're in calculus, and you're a senior in high school. I didn't take calculus until my second year of college. I know. And then I majored in math, so I was way behind. And you know what? I loved my 5.5 years of college. They were so fun. Mm-hmm. Took me 5, and I'm not a doctor. It's weird, I know. Those are doctors. Okay, here we go. What's the rush, though? Once you get out of college, then you have to work. Oh, no, I didn't have any debt. I went to state schools and JCs, and it was cheap. All right, let's take the derivative. Here we go. We need to find any, minus. We need to find any local extrema, intervals on which the function is increasing, intervals on which the function is decreasing. So let's take the derivative. Derivative 4, 0. And then this right here, we need to change this. Yeah, there we go. I was going to write negative, I was. All right, so bring the 1/2 down. So I was like taking the derivative already, huh? Bring the 1/2 down and then subtract 1 off, and that's where you get that negative 1/2. So the derivative would be negative 1 over 2 rad x plus 2. Oh, yeah. It's a little problem. I forgot. You have to figure out, nothing will make this 0, but we do have to figure out the critical points. And in this case, the critical point would be x equals negative 2. Because that would make it undefined. Yeah. I'm glad that you gave me this one because I forgot to mention that.
Me too.
Yeah. So set the derivative equal to it's being undefined, which would be 1 over 0. And so if I plug in negative 2, I would get 2 over 0. The thing is, though, oh, okay. Yeah, that's interesting. All right, so let's go ahead. Oops, I didn't mean to draw that middle line. And negative 2. All right, so now we're going to test the derivative. Here's the thing, though. When you plug in anything...
Wait, if it's an absolute function, that means like they're not on the other.
There's what?
There's like nothing, they only come on one side, right?
If it's
a
square root, yeah.
Is that
So, and you can think of the original function and do it that way, or you could do it this way, and when you start plugging stuff in, you'll see it too. So at negative 2, it's actually an undefined derivative. So let's plug in x equals negative 3 into here, into the derivative, f prime of negative 3, and you can't. You get imaginary numbers. So there's nothing over here. There's no graph. And you knew that, right? What was the original function? It's the square root of x plus 2 and then shifted up 4. And you know that the domain of the original function is nothing can be negative 2 or less. Well, let's see. Is it increasing? So let's check it out.
0?
Yeah, let's plug in 0. Yeah. So you plug in 0 and you get negative.
Wait, what?
F prime of 0 is negative 1.
Negative.
It's a negative 1 up top.
Negative square root.
2 rad 2.
So it's decreasing.
So it's negative. So it's decreasing. I'll show you the graph in just a minute. So this one is decreasing from negative 2 to infinity. If you were to graph this, you guys know your basic parent function for a square root looks like that. Maybe you don't, but that's what it does look like. And this one is being shifted 2 to the left and 4 up, but the negative in front reflects it over the x-axis.
So do we need to
Okay.
make our critical point?
Well, yeah, you need to say what the critical point is. I'll show you that in just a minute. It's undefined, the derivative's undefined, but it actually is a critical point because it's actually an endpoint of the graph. So I'll show you. So if you have negative, it flips it here. This is shifted 2 to the left and 4 up. So this is what the graph looks like. Okay? So this graph is constantly decreasing. Every single thing here, the tangent line has a slope. It's negative.
Wouldn't it be not the bracket, but the negative 2?
No, they want the bracket though.
I thought it was an open circle.
Yeah, the derivative doesn't exist there.
Oh.
But the graph, the original function does exist at -2. And that is actually a maximum of the graph.
If we put a parenthesis on accident,
I don't really mark off for that, no.
so
Okay.
then to find the critical point, we just
Mhm.
plug a negative to the original function and get 4.
Yeah. Yep. So if you wanted to find what that point was, that's -2, +4. It's a maximum value. And then think about this. If I'm undefined on the left, so if I have a graph that has nothing going on the left of my point, but it's decreasing on the right-hand side of it, isn't that still a maximum though?
Yeah.
So there's nothing going on and it's decreasing on that side, it's a maximum graph. We talked about them when we had endpoints. Bless you.